Hello everyone, and I am Udiptya, uh, PMRF scholar from IIT Madras. So now we will be discussing with the problems related to the week 10 of the course Fundamentals of Micro and Nano Fabrication. So hopefully you all have completed seeing the videos. So uh, so this week 10 primarily like broadly dealt with the topic of dry etching, and so it was divided into 5 videos, and the first one was on purely on how the plasma is and the properties of plasma and how it is generated. The second video was on how to use this plasma for etching. The third video was on the configurations or the technical like technical specifications, how these are used and how like in the state of the art state of the art devices or systems. And then we got to know about the etch mechanism. So uh, so it's now we saw that in deposition also, that we are depositing materials. So here the mechanism is we are removing the materials, and how to do that, because depositing is something that is that can be considered like easier than like removing it. Removing, you need to be very selective, and how these are removed, that is something that we discussed in the etch mechanism. And then the etch chemistry. So primarily this how the selectivity is brought in this etching system, and uh, the majority of that is something that is related to the etch chemistry. So etch chemistry is something that has kind of a big role in how this etching is done using such selectivity. Okay, so kind of that was what crux of the videos that we dealt this week. So we will go to the problems directly. So this is a problem. So we have a figure is shown, and that involves a graph which is uh, like on the y-axis it is the breakdown voltage, and then on the x-axis it is the pressure. So so you have to tell, so this graph is also called the Paschen curve. So you have to choose the incorrect statement here. Okay, so these are the 4 statements, and you have to tell which one of them is the incorrect one. So you can write your answers in the chat, or you can also unmute and say. So that's all. D. Okay, so remember, you have to tell the incorrect one. Yeah, so that is one. A. Okay, so anybody else wants to answer? Okay, so B. Okay, cool, no issue. So okay, so in this graph, you see the pressure increases this way. Yeah, this is, so this is the high pressure zone, and this is the low pressure, and this is kind of the moderate. pressure. This is the high one, high pressure. So like at very low pressures. So we can see like what kind of how the plasma is generated here. So essentially we have two electrodes, yeah, and we have distance, that is here it is given 0.1 inch gap, so such that, and we have a potential such that this the uh, the like the air or any dielectric that can be broken down such that it can current can flow through it, yeah. We have to ionize it. So essentially here as it has, see this graph has also written this that this air is zero 0.1 inch gap. So essentially if we change the gap of air with the same pressure and same breakdown voltage, like the breakdown voltage would differ. So that's the result. Such graphs also come with the specified gap also. So that's the thing. So essentially the breakdown voltage is a function of both the electrode gap and the number of molecules. Okay, so electrode gap is something such that I told this is the D1, and the number of molecules we can think like how much is the pressure. So like depending on the pressure, so if we are going at low pressures, the number of molecules will be very less, while in the pressure, in the high pressure domain, essentially the air pressure would be more, and therefore the number of molecules will also be more. So this is a correct statement kind of, but we have to find the incorrect one. So at high pressure so we are going from the last, okay. So at high pressure the electrons lose energy through collisions. So yeah, so at high pressures what we have is more particles, and thus when the electrons are generated, they get scattered due to the like large number of collisions, and they lose energy due to this collision. So this is also a correct one. And at moderate pressure, where the breakdown voltage is low, there is an optimum balance of charge lost through collisions and sufficient amount of molecules for charges to interact. So this is this one, the kind of ideal condition for use of the generation of plasma. So this is also correct. And the last, the A option, that at very low pressures complete ionization takes place and results in presence of free electrons, and these free electrons repel the cd electrons, and the breakdown voltage rises. So essentially the breakdown voltage rises because the like the uh, here the molecules are less, so that's why we have higher breakdown voltage, okay. So this is the incorrect one, okay. So this is the problem 2 uh, that we are discussing. If you have any doubts in the answer questions, you can ask. If you need more clarifications, you can ask. Okay. So this is the problem 2. So in a plasma chamber, argon gas was fed, and the plasma glow of dark red color at wavelength of 696 nanometer was detected. Okay, so you have to find what energy level difference that the electron had transisted to emit a photon. So essentially, how this emission of light happens in during plasma, so that you have to recall, and then you might be able to like solve the problem. So this is the process that gives color to the plasma. Excitation. So I hope you all are trying the question, yeah. Done. Okay. Let's simplify how the things are happening. Yeah, sure. So essentially, you can consider you have a atom, okay, and we have an electron here. So what happens is that when we bombard it, the electrons. So what when it happens that when electrons are bombarded to the argon, what happens is that they attain a higher energy state. Okay, so these electron goes to a higher energy state. Okay, so so essentially this is the inner shell and it comes down to the outer shell, and so you can consider this as A and this as the A star, and when this when from this A star excited state, this is the excited state, it comes down to the ground state. So essentially this is the ground, and this is the excited, yeah. So excited and ground. So when it comes down to this, emission is in the form of H into a photo emission is there. Okay, so essentially if you see it, it is like that this electrons plus A is giving this electron is there only, so it is giving A star conformation, and then this A star is coming down to H nu. Yes, so this H nu is essentially the wavelength of light, the light that you are getting. Okay, so this is the basic concept that is going on. So yeah, so now we want to try this, or should we go directly to the answers? So essentially the energy that is there is it's C by so it is basically the Hc by lambda, yeah. This is the energy, and you can for simplification this Hc you can take as 1240 electron volt into nanometer. So this is something that you can calculate and get it. Sorry. So let's try. You try. Just. So this HC, you know, and we have to put the lambda. Essentially, that should be the energy that is emitted when the like the atoms go to the ground state after excitation. Okay, you all are trying, or should we go? 1.78. Okay, let's solve it. I also have to solve. Okay, let's see. So we have 1240. Okay, and essentially electron volt into nanometer, and then 696. Okay, so essentially you have to divide it. So okay, yeah, it's what you have to 1.7. Yeah, so this is in electron volt. Yeah, so you can see like whenever they have some like this photo and energy conversions, you can use this, like it is something that it will be very handy actually. So while solving, you will find it easier, because if you do it in joule and then come into electron volt, in some like exams it can like take up a lot of time, and plus if there is something that is objective, so this is something that can come in handy. Okay, anyways, any doubts, or should we go forward? Okay, we'll go over. Sure. So here this is a multi-correct uh, question regarding the plasma process. So four statements are given. You have to tell which one of these four statements are correct. So this is a multiple correct. So multiple of them can be correct. And yeah, that's all. So any options you are not clear about, you can ask. Okay, C. Okay, so it's the only correct. T. Okay. The other options? Anybody? Other options are incorrect. Or that's all. C or C and D. Okay. Uh, anybody else wants to answer? Okay, B. Mhm. Okay. I hope that's all. Your B, C, D. Yeah. Anybody else wants to add or delete something? Okay. So the first option is essentially wrong because the product should be volatile for deposition. Uh, Essentially, we are talking about plasma process, and it shouldn't be like we used plasma process for deposition. Essentially, the product that needs to be deposited should not be volatile, and essentially should be there in the place where we want it to be deposited. And like this statement, if it was been for etching, it would be a correct one, but essentially here in this case it is wrong. Okay. So, and the second one, inside a plasma chamber, the argon gas is used to dissociate into reactive free radicals to make noble argon gas react chemically with substrate for etching of materials. Essentially, this for etching, we essentially use this reactive free radicals, and argon gas is something that is inert. Essentially, argon is used to uh, to get this to get ionized, and this ionization process helps in generating of electrons. So argon gas is used in plasma for this production of like generation of electrons rather than chemically reacting it, because it doesn't essentially doesn't chemically react with any substrate, and for that we need some uh, reactive gases that helps in like which then breaks down into radicals, and they essentially etch the materials, and like in place of this argon essentially is something that takes place role in ionization, and ionization for that's the like next question. Yeah, next option, that ionization process is important to maintain the plasma, because this helps in this argon helps in this ionization process, and the plasma is maintained because the electrons are being generated. So this is the correct one. And dissociation of molecules into reactive free radicals. So this they collide with the molecules, and they dissociate into dissociate to radicals, and these radicals go down to the places where you need the etching to be done, and they chemically react to that surfaces and remove, such that and the removed the where it reacts, it generates volatile products, and that's why it is being removed from the surface. So C and D are the correct ones. Okay. So I hope it is clear for you all. Yeah. Then we can go to the next one. Okay. Okay. Let's proceed then. So this is also a numerical. Uh, so in a DC plasma chamber, the voltage applied is 200 volt. Okay. And the plasma potential is 5 volt. So you have to tell what is the energy of the argon ion that arrives on the substrate. Okay. So I hope you all are able to visualize the problem. Okay. So I will help you visualize the problem here. So in case of DC plasma, what happens is we have two plates actually. Yeah. So one of them is grounded, and essentially the other one is at a biased voltage. Yeah. So this is ground, and and at this place we have plasma. Okay. So what happens is that so we have this we told that the voltage applied is 200 volt. Essentially this is the 200 volt that we are applying, and this is the V plasma potential, that is the so this Vp equal to 5 volt. Okay, now you have to tell how much like we have to so you can see that the for the argon to be has to move from here to here, so you have to tell how much energy it would attain when it goes to uh, this this complete path. Okay, so that's essentially is the question. So this positive ions will be created here, and it will be pushed through this zone and come to this. So this is the kind of breakdown of the question there. Now you all want to try. Okay. I'll basically these positive ions are like created here at this place, and they are accelerated, okay, and towards this electrode, okay. And so that essentially the energy, so the potential difference is the sum of the accelerating voltage that you can take as this 200, and the plasma potential. This is the, because it encounters that also, yeah. After it is being produced here, due to the 200 volt high, that high voltage, it has to cross the plasma potential also. So the plasma potential, and essentially the electron, yeah. So E into this V. So that is basically the energy. That is so this is there in your the slides of this DC discharge also. So essentially you will get E into 205. Okay, so it is essentially 200 205 EV. Okay, so that will be the answer. Okay. Okay. So for more, like you can see how these things differ in RF and DC. And I think I forgot this. Maybe in plasma etching basics, you will find the differences in both of this. Okay. So this is problem 5, and this is a question from ICP etching system. So it is inductively coupled. Uh, so, so sorry, I got a call actually. Uh, uh, so this is a ICP means inductively coupled plasma etching system. So we have a inductive kind of, here that last question we were having a DC or RF kind of, yeah, generation system, but here we will have a kind of inductor that helps in generating this plasma. Yeah. So okay, you told B, yeah. Okay. Okay, any other answers? Okay, essentially this is a single correct one. So okay, anybody else wants to answer, or you want to change your answer? That is also not an issue. Okay. Can you explain in brief, like why you think this option B is correct? Okay, just graphically, I will okay, let's do it like this way. Okay, so essentially in ICP etching system, what happens is we have a kind of a dome, and we have coils, yeah, and so essentially the coils are here, and we have the place where we want to have our etching done, and this is have a maybe have a bias. Okay, bias voltage is there, and so essentially this is the plasma potential, and we have this so essentially plasma is produced here, and it is coming for etching here, yeah. So what happens is that okay, so there are two factors here. Okay, so essentially there is the source power and the bias plate power. Okay, so essentially source power is something that helps in generation of ions, generation of, yeah, the plasma, and essentially the ions. So with increase in source power, what we do is increase uh, the number of ions that is generated, or the density of the ions, or what basically we should say the ion flux. So with the source power been increasing, the ion flux increases. Okay, and it is like wonderfully it has been shown in the graph also. Yeah, one graph was shown that has I think the ion energy in this side. Okay, and this is the source power, and this is the ion flux. So the ion energy, this is the ion energy, and this is the ion flux curve. Okay. So essentially, like this is at constant bias plate power is constant. So what we see is when we increase the source power, what happens is that this ion flux increases, yeah, but the thing is the ion energy that decreases, and essentially this diagram explains the answer to the ion energy. Essentially the ion energy decreases because of high source power, and you can ask like why. Because is that uh, essentially for the uh, so this what energy it would this ion energy would be there, like ion would be bombarded to the substrate, is derived from the potential difference. Okay, so if the source power is going high, what happens is the potential of the plasma also goes high, and essentially this decreases this potential differences, and what we have is less difference between the like this plasma and the base plate, and what happens is that the ion energy, that acceleration thing is low. So we essentially with high source coil power, we essentially get less energy. And if you like in this kind of questions, all kind of like most of the kind of the permutation combinations, like what happens with the ion energy, what happens with ion flux, and all this can be derived depending on, like, this diagram is only valid for the source power. Same diagram is also being provided for bias power, like like how, and that's how we choose like what kind of like bias power we should have, and what kind of source power we should have, and that's how they tune these systems. Yeah, so essentially the answer would be that high source coil decreases the energy, like this one. Yeah, it is decreasing due to the source power. Okay, So if any doubts you can ask, otherwise we'll go to the next one. Okay, sure, we'll go. So I have also given the answer here. So if any doubts, you can also refer to the text here, or also you can I'll be uploading the PPT. So essentially, you can also go through this. Okay, problem 6. Then we're going to problem 6. Okay, so this is the problem 6. So this is about a incapacitive etching system. So this is a question from the configurations that I told you, plasma etching configurations. So in capacitive etching system, it was found that the etch rate of all materials is same. So they were finding that the etch rate of all the materials are same, and you have to find why this was a issue. And this kind of this issue this issue can help, like we learned about a lot of configurations here, and out of that only some of the configurations are usable, and others are may not be usable for this etching purpose, may be usable for other purposes. Yeah, so that's why so you have to tell which one of them is such a system. Okay. Okay, so let me draw the different etching systems here. So let's start with the single frequency one. So it consider it to be a chamber, okay, single frequency and 2 electrode system. So you will have 2 electrode, this will be RF, RF, and essentially this is single frequency. So the frequencies are same, gas will flow like this. Okay, and this is grounded. So this is the option B. So and then the next one is lower frequency, like dual frequency, different frequencies. Yeah. So this will be like grounding and RF1 and RF2, and the lower frequency in the, so RF2 is lower and gases, and then this one RF1 and RF2. So they switch between the systems and gases. So Okay, there will be a gap here. Okay, so this is the cases. So the thing is, the single dual frequency at use of dual frequency at the bottom electrode to control both the ion. The first option, yeah. So essentially, dual frequency is A, and this is the C. So the thing is, so in this, so now you have to tell that you have to choose a system which is less controlled one, yeah. So here you are getting two electrodes, and we can choose the RF frequencies, and depending on it we can generate the ions and control the ion bombardment and ion energies and ion fluxes. And because there we are using two different frequencies in this A and C options, the control is much. Okay, while in the option B, where we have this the frequencies are like frequencies are same, the control on the ion energy and ion flux are very it is very difficult to control, yeah. So and what happens is that we get in this condition of condition of B, we start getting sputtering. So that's why this thing is not a very not an ideal condition for etching, but this same configurations are used for etching systems. So you will find the use of dual frequency and use of lower frequency in like differential frequencies in both the electrodes, but the single frequency is something that is common with the etching system, the deposition systems, basically because it sputters the things. So essentially, option B is the correct one. Okay. So it's all about the control and how we can control both the ion flux and energy. Here, as we have only same frequencies, it will start sputtering. Okay. The selectiveness is not there, because if it starts physically this ion, if it bombards, so we are going to physical etching, but the thing is we want chemical etching because it is more selective here. Okay. So this is problem 7. So chlorine, Cl2 and CCl4 gases, so tetrachloride and carbon tetrachloride and Cl2 chlorine gas are aluminum etchant. So which of these is true? You have to tell. So four options are given, and you have to tell which one of them is true. So it is a single correct one. Any answers? any answers you want to like to try, you think is correct? B. Okay. Okay, we'll go. Okay, essentially, we will see the cases in detail then. Okay. Uh, Essentially, when Cl2 is used, it etches aluminum. It etches as aluminum isotropically. Okay. So by isotropically means it etches in all the directions equally. But the thing is, the thing is when we use like argon ions also, essentially it is kind of the same profile that we get. But when we etch it through CCl4, what happens is CCl4 like we told about this dissociation, yeah. So CCl4 like breaks down into some form of CClX actually. Okay, and what happens is that like consider that this portion is there and this is the mask you have. Okay, and you start etching it. So what happens is that that the CCX forms kind of a polymer on the surface of the side walls actually. Okay. And this helps in getting this straight anisotropic profile. So essentially uh, CCl4 has this kind of forms this polymer and helps in getting this anisotropic nature. Also, you can think that like the like this they have proved this that when by changing the flow of the angles of the argon ions also, so this essentially this they have proved that this kind of polymers are formed on the sideways. So this is kind of they helps, this is what directionality helps, yeah. So this way we get term directional etching. So directional etching is how the etching, what is the difference in etch rates between the horizontal and the vertical profile. So if the vertical profile is like whatever way you want to direct, so that should be in a measure form. So that is the measure of directionality, yeah. So here essentially chlorine neutral species etches aluminum by physically bombarding it. Okay, that is not which CCl4 etches AI isotropically. No, it doesn't etch isotropically. Uh, so this chlorine neutral species. So it basically this radicals etches the aluminum by physical bonding, and so this is wrong. This is wrong, and the argon ion significantly enhances anisotropy of aluminum etching by Cl2, no, because they doesn't form this kind of polymers there, and that's why it doesn't enhance any anisotropy. So only in the form of CCl4 we get a polymer that I told here, and in the side walls, and that results in such directional etching. So this is the correct one. Okay. Okay, so we'll go to the last one. Yeah, this is a short one. And this will be the last question here. So you have to tell, as we discussed, the directionality. So how the temperature plays a role in directionality of edge. Just a simple one, and then we will close the session. C. Okay. Okay. Let's go to the answer then. Yeah. So essentially, what we see is that these radicals come to the surface and they react and they etch out the material. Yeah. So that's the kind of thing that happens. Uh, so what is so with temperature, what happens is that, like, let's see the diagram. Yeah. So this is the mask, and this radicals are coming. What happens is that when it is in surface, uh, think that it has come to the surface, with increase in temperature, what happens is that they start diffusing, and diffusion is not is something that is not a directional phenomenon. Yeah, these things can diffuse in any way, in any of the ways. Yeah, and that is not something that we can control. Okay, so we essentially decrease the temperature such that this diffusion of radicals can be controlled. Okay, because otherwise it will diffuse and it would etch out these portions. Yeah, and it would result in like kind of isotropic profile. It would start inducing the isotropic profiles. So essentially we decrease or lower the temperature such that we get a kind of these radicals are not diffused, and these are kind of inbound with what area we want to, and then that's how we control its reactions. So uh, essentially that you told. Yeah, I think what you told, at low temperatures. Yeah, but the main thing is uh, because at low temperatures these things are there, option C that you told can easily remove the material in vertical directions, but diffusion is one of the important things that doesn't happen at low temperatures, and is a big contributor, kind of plays a significant role in the reactionality. Okay, so that's all for today, and thank you for coming. And if you have any doubts, you can write to me, and uh, uh, and then we will discuss it in the next class. Okay, and so I'm now closing the session. If you have any doubts, you can stay, and otherwise, so you're free to leave.